All right, everybody, welcome to week 7 of Geography 473, 673. This is the last week for tutorials before we dive into the final project. And this week is about SciPy. So, SciPy, scientific Python, and it's a collection of mathematical algorithms that are built on top of NumPy. And there's a lot of different things that we can do with SciPy, from different statistical analyses to creating algorithms and using algorithms to running fast Fourier transforms, interpolations, linear algebra. There's a lot of different mathematical functions that we can employ from SciPy. So I have a little bit of text right here. You can read more about SciPy, and then here's some sub packages of SciPy. So SciPy is a pretty large package, and there are sub packages of SciPy. Now, don't worry, when you install SciPy, you install all of the sub packages here, but these different sub packages, they have some different functions. So you have a spatial sub package, so SciPy.spatial, which has spatial data structures and algorithms, and you also have stuff like FFTPack, so fast Fourier transform routines that you can use from SciPy.FFTPack. So there's a couple different sub packages that you can learn about, and a lot of times what we'll do is we will read in these sub packages with a special name. So remember that from the MetPy tutorial, for those of you who tried the extra credit portion, we imported SciPy ND image as ND. So that is just a traditional way to read it in. That's just kind of a popular way. That's the way most people read it in for a sub package. So there's different ways you'll see out there as you browse this code, different code online. So, but here's a SciPy cheat sheet. So it has some different examples, different things you can do with SciPy and its different sub packages. But really what we're going to do today, and this is a shorter tutorial relative to the other ones that we've done, but this is really about oceanography. So we're going to dive into some ocean data today, and we're going to make this plot, and then we're going to use those skills to use down here in the assignment. So the first thing I'm going to do before we get started is I'm going to open up my Anaconda Navigator. I'm going to head over to my Geog 3.8 environment. And I'm pretty sure SciPy is already installed, so we shouldn't have to worry too much about that. It's a really popular package, so normally it's a dependency for other packages. We'll find out, and if it's not installed, then we'll go ahead and install it. All right. All right, let's see here. There we go. Okay. All right, so first thing I'm going to do here is I am going to load in a new file right here, and then I'm going to copy over the first part of this tutorial. So we're just going to be loading in a netcdf file that has a really ugly name. And notice that we don't need SciPy just yet. We're not going to load it in just yet. But the file that we are going to be using here right. So the file that we are going to be using here is called this ugly name right here, ORABIL2. And what this is a GOES 16 data set. And so for those of you who don't know, GOES 16 is the geostationary environmental observing satellite. And it is an amazing satellite. It offers some very high temporal resolution data. And one of the products that it offers is a SST or sea surface temperature data product. So that's what we're going to do. And we went ahead, loaded up these packages, and we opened the file, and we loaded it via Xarray. So now we can print that out, and we can see that we have latitude, longitude, time. We only have one timestamp, so this is just a snapshot of the Atlantic Ocean. And we notice we have some different data variables in here. So band 15, DQF, SST. So band 15 is actually cloud cover reflection, and if memory serves me, band 15 is actually going to be a long wave band. So it's in the long waves point of the electromagnetic spectrum. So this is just different reflectivities that we're seeing back from a remote sensing satellite. And DQF right here, this is called data quality flag. So DQF is paired with SST. So in the SST, we have all these different sea surface temperatures, but clouds get in the way. And we can note, what we'll notice is that when we actually go ahead and plot all of this, what we'll see is that the SST is way off where there are clouds. It is completely underestimating the actual sea surface temperature because a cloud has intercepted that sensor reading, the reflectivity, and it will show up a lot colder than it actually is. And we'll see that as we go ahead. So band 15, yep, it's an infrared long wave band. And if we just actually wanted to take a look at it, so this is just that band. So now we just selected, so we have a data array from our Xarray data set. So, and it looks like this. It is a brightness temperature. That is the unit that we're checking out here. It's a brightness temperature. And if we wanted to select the 0th index, aka we only have one timestamp, so there is only one value down here. So now our time is selected. It is from July 27th, 2019. Our units are in Kelvin. Remember, this is brightness temperature. We can check out the latitude and longitude values. And go ahead and check those out. And yep, and what we know from this data set is that this projection is plate carry. So this data set has been reprojected, and it is now a plate carry, and it has been reprojected from the initial data feed. So the data feed that we are getting this data set from is already reprojected for us before we even have to load in the file, and it is plate carry, so it's just a lat long grid. So what we're going to be doing here is we're going to plot everything up the old-fashioned way. So we know the Xarray shortcut to plotting. We've done that a couple times, but now what we're going to do is we're just going to plot this up the old-fashioned way, aka using P color mesh. So right here, this is the line that does all the plotting, ax.p color mesh. We have our x values right here, so our longitude values, we have our y values, our latitude values, and then we have our z, or what is going in our axes, which is the Ocean SST band 15 0th index values. We're choosing a color map of jet, and we're just transforming this. This is redundant, we don't need to do this, but it's just good practice. So we're transforming this to CCRS plate carry, and we have a Vmin of 250, Vmax of 300. And remember, the units are degrees Kelvin, so that's where we're going here. So we're going to plot up this band 15 using this code. So let's just look at it just using that initial part right there, highlighting. I'm going to run that. Go to our plots, and that's what it looks like right there. That's the data. This is the mosaic. And now what we need to do is we need to add in some coastlines, some borders, a color bar. we're going to add in values of latitude and longitude from our initial longitude and latitude values ourselves. So I'm going to copy all that I didn't right here, and I'm going to add that just like that. And now if I go back and highlight all of this, be the same image, but we're going to add in a little extra detail here. So now what we get is our longitude values, our latitude values, a nice title, band 15 brightness temperature. Now we have our color bar over here. And so right away what we can see from this image, and maybe it'll look better if we look at it over here because it's just a little bit larger. So what we can see is we can pick up pretty quickly that, okay, these blue things look abnormally cold relative to everything else. Those are clouds. That's what we're seeing. We're seeing cloud top reflection. And so the temperature of a cloud is much, much colder than the temperature of the ground or the ocean for that matter. So, and why? Because clouds can be anywhere from, 5,000 to 60,000 feet, depending on the type of cloud. So really even 1,000 to 60,000 feet. So what we're seeing here is just clouds are colder. And so they're registering as colder on their brightness temperature. So we have this right now, but what about sea surface temperature? So now we'll actually go ahead and we'll use our Xarray plotting function instead. So we will just use the easy method for sea surface temperature. And I'm going to refer to sea surface temperature as SST. So go ahead and remember we're just going to go grab our 0th index. It's a little bit redundant, but that's just the way we have to do it so that Xarray can recognize the data array structure. Then we're going to plot it with a jet CMAP and a new Vmin of 273 and a Vmax of 300. Highlight that, click run. Still processing, and there we go. So this is sea surface temperature. So what we did was we plotted up. There's actually data underneath this coastline. It's all invalid, right? Because you can't register sea surface temperatures over land. So it's all invalid data. And that is where the data quality flag comes in. It comes in there. So if we didn't have this coastline and this filled land right here, so right here we're filling in the colors of everything. And what we're doing here is we just overlaid this over top of the data. And now even if we didn't have this covering everything up, we can use the data quality flag to do that for us. So the data quality flag has bad data over land because there's no SST data over land. It also has bad data where there are clouds. So we notice right here, we kind of notice, okay, these are a lot colder. The water does not get down that cold in this part of the ocean. And remember, where our Vmin is 273, which is 0 degrees Celsius, aka 32 degrees Fahrenheit. What happens to water at that point? It freezes. So we know that there's something going on with this data, and this is where the data quality flag comes in. So the first thing that we can do here is, instead of using that nice data quality flag, let's check out and see if we can use our band 15 as a data quality flag proxy. So we're going to use the .where function. So we're going to say, okay, my ocean SST, it's going to be a new data array that I'm creating. It's going to be ocean SST variable where ocean SST band 15 is greater than 280 Kelvin. Now, this is just we're going to see if this works. Let's see if it works. So we're using band 15 as a threshold instead of data quality flag. You guys will use data quality flag for the assignment, which is the proper way to do it, but let's see if we can do it our own way. So we're going to plot SST with a quality controlled band 15 variable. And this is all we need. We say, okay, we know that our Vmin and our Vmax from this photo this image was 250 to 300, and we're just saying, okay, only give me the values over 280. And this is just an arbitrary number. You can choose this to be whatever you want, but this is a more conservative routine because we're just saying that, okay, anytime there's temperature values, brightness temperature values below 280, we're going to mask those out. So we are converting all of those to NA by doing this. So we're controlling that right now. So now Ocean SST, notice we have a bunch of nans in here now with our new data array SST, and that's because we masked those values out with the .where function with the condition inside. So notice that Ocean SST is now only the SST variable from the original data set. So that is why we shifted from an Xarray data set to an Xarray data array, because we only have the SST variable. So now we can plot up our cleaned SST image. So same code as up here, only our input is now going to be different because we adjusted the Ocean SST variable. So now I can go ahead and I can run this because we cleaned up Ocean SST. Now we're going to go from this with these ugly clouds to this where we mask out all of those clouds right there. So now this is a much more reliable data set. So, and I'm not entirely sure why the colors aren't working. Maybe they updated that code. That should be gray. Let's see if this works just really quickly. And to try to do something there. So not the best, not exactly what we want. We can revisit that later. But basically, I guarantee you it's a version of CartoPy problem right there because these features are coming from CartoPy. But at any rate, all we did was really, if we just take a look at the underlying data right here, we got rid of the clouds. So we were able to mask that successfully. So the big thing here, and the big thing about this entire tutorial, is that SciPy is working underneath of Xarray. We might have used Xarray for all of this stuff, but like we said before, Xarray is a high-level package. It's higher level than SciPy. So there's a lot of redundancy, and there's a lot of things that are happening underneath the hood that we don't see. And some of these examples, like right here, where we use the .where function, that is built on top of SciPy. So this is just a good package to know about. Unfortunately, we don't have time in the class to actually go into further detail on some of these other sub-packages, but really, it's just a good package to know it exists. So now that we used band 15 as a cloud mask for the assignment, what we're actually going to use is the DQF variable instead. And I talked about this earlier. It's a data quality flag, and it has grades for each grid cell value of SST. So we have 0 is a good graded cell, 1 could be good, could be bad, but the algorithm is unsure. 2 is a bad graded cell, and 3 is a land graded cell. So now what we're going to do is, instead of using this right here where we say Ocean SST band 15 greater than 280, those are the only points we want. We only want the DQF when it equals 0. And then I want you to plot everything up using p-color mesh. So remember, the old-fashioned way, the more customizable way, as opposed to the Xarray version. And then just submit that to Canvas.